Thanks for the introduction. How does it sound? Good? I'm known to be a loud talker, so just let me know if I get a little too rowdy up here. So my name is Dakotah Tyler. I am a PhD candidate in physics and astronomy at UCLA, and I study exoplanets. And today I'm going to talk a little bit about what we know about exoplanets. It's pretty interesting, the arc of discovery that we have, and some connections that I've made with my own life, which has been full of some surprises as well. So I think, all right, so we got the screen coming up here. Now, I do want to say this. So there is a Q&A at the end, but I like to be engaged. I have like that kind of ADHD where I want you to ask me things throughout. So at any point in time, if you have a question about anything that I say or something that's even tangentially related, we'll allow that. Just ask. And the light's kind of bright, so I may not see your hand, so feel free to just, well, try to wave me down, try to get my attention. But ask me any question throughout, and we can chat about whatever it is that's on your mind. So yeah, DT Star Kid, this is my name on socials, and I love doing science communication. I love engaging with people and just making easily understandable all the things that we know about the universe, which is really amazing. We live in a crazy time where we know some things about the universe that for 99.9% of humanity, people were just guessing. They were kind of just making up stories about how we got here and what else exists. So one of the things that I'm going to talk about today is evolution. So everything in our universe evolves. Everything. The universe itself, stars evolve, they form, they live, they die, planets evolve, life evolves, you evolve within your life, and our understanding of all these things evolves as well. And one of the types of evolution I'm going to talk about is exoplanet evolution. So this is what I study. This is what I'm actually doing my dissertation in, the evolution of exoplanets. Now, exoplanets are just planets that orbit other stars. So to some other alien astronomers in another star system, the Earth is an exoplanet, right? Just planets that are orbiting other stars. And we know of almost 6,000 right now, which is considerable because back when I was born, 1990, we didn't know of any. We didn't know of any exoplanets. So there are some people in this room, including myself, that are older than my field. And then, of course, there are some young people who are always going to know that we know that there are hundreds of billions of planets just in our galaxy. So the thing about exoplanets is that, again, if we roll back the clock a little bit to when we didn't know much, we knew about our solar system, right? Our solar system is like surprisingly uniform. It's pretty organized. Everything seems to orbit in the same plane. We got 4 small rocky planets that are closer, and then there's 4 larger gaseous planets that are mostly atmosphere that are further away, and everything is like nice and ordered. Of course, with the exception of Pluto, which is a little bit bigger than the state of Alaska and has this kind of wonky inclined orbit. So it really kind of like shirks the uniformity of our system, of our solar system. Of course, we came up with an elegant, we came up with an elegant solution for that by just getting rid of Pluto. So Pluto's not a planet, it's a dwarf planet. So the statement stands, our solar system is very uniform, it's very organized. And we thought, of course we did, we thought when we looked out at other stars that we would see planets that were similar to ours. We thought we would see systems that were very similar to ours. We took our one data point that we thought we knew pretty well, and we just extrapolated it out and said, hey, we're probably going to find systems that have close-in terrestrial planets, some gas giants, which we call Jupiters, and then these smaller planets that we call Neptunes, which are a distinct category from the gas giants, a little bit smaller, but still mostly atmosphere. Now, I do have one thing to say is that, one of the differences between the inner planets and the outer planets, please just somebody like give me an observation between those four sets of planets, each of the four sets. Yeah.
The gas giants they're more gassy.
They're more gassy, right? And gas is light, right? So if you want to hold gas with your gravity alone, you got to be very, very massive. So we find that all of these planets are beyond what's called the snow line, or the frost line, the ice line. Basically anything close to a star, something like water or some of these gases are going to be liquid or gas, but they're not going to be solid. If you get further away from the star, some of the things that are gas when they're hot are actually going to be able to condense and become solid. So basically, the further away you get from a star, the more stuff that you have, the more dense stuff. You can accrue more mass, which allows you to collect even more mass and more stuff, and eventually start eating up a bunch of gas. So we have this sort of first order understanding of how planets form, where close planets are small and rocky, far planets are large and gassy. For sure, when we look out, we're not going to find any gas planets that are close to the star. That doesn't make any sense because that's not what we see in our solar system. Of course, the first exoplanet that we find orbiting a sun-like star is a hot Jupiter, which is not anything that anybody even thought could exist. It wasn't like, oh, well, we find these might be rare. Astronomers had no idea that this was possible. How do you get a Jupiter-sized planet that's on like a 3-day orbit around its star, completing that orbit in just a couple days? This was a mystery. This was like a huge news. Not only did we find an exoplanet, we found planets somewhere else, but it was something that nobody thought was even possible. Of course, this is because we're just thinking about these systems based on this one data point that we have, this like very slim understanding of what things could be. Well, okay, so how do we explain this? How do you explain these hot Jupiters, which we didn't think could exist before? Well, maybe what happens is these planets do form far out. A Jupiter-sized planet does need to form really far away from the star. But over time, something happens where it gets knocked on like an eccentric orbit and it like slowly migrates inward and gets closer to the star over time. And if that process could happen, this migration with a planet as massive as Jupiter, then we start to form this new theory of what's going on, and we just predict that, well, okay, if it's easy for gas giants like Jupiter to migrate inwards, we probably won't find any small planets that are really close to stars. Like if this migration process is so effective that it can bring the Jupiters all the way in, surely small planets would either get eaten up by the stars or just kicked out of the system. So we continued to look, and we expected to find no small planets close in, and we were wrong again because we find that the most common planets in our galaxy are actually between the sizes of Earth and Neptune. And one of the big takeaways from the Kepler mission is that most sun-like stars have a planet in between the sizes of Earth and Neptune on an orbit that's closer than Mercury. So most of them are like within 50-day orbits. You've got this planet that's either a sub-Neptune or a super-Earth, a little bit smaller than Neptune, a little bit larger than Earth, and on an orbit that's closer than our closest planet. Now, interestingly, we don't have a planet like this in our solar system. So we were almost wrong from the beginning, assuming that we lived in an average system, which I think is a safe assumption to make. I know we all want to feel special, but statistically, we're all probably pretty average. And when you think about astronomy and you think about the sheer numbers, it makes sense to assume that what's going on near you is kind of going on everywhere. But that's clearly not the case, and we're not totally sure why we don't have a planet like this in our system. We're still trying to figure out the exoplanet formation process. So, okay. Now, here's the demographics picture after we find 6,000 planets. we're really at like 5,600, but we're getting close to 6,000. So we've got these hot Jupiters up here. And I guess this, just to explain this plot, we have planet size on the y-axis in Earth radii. So here's a line right here that shows you the size of the Earth. Here's Neptune, Saturn, and Jupiter. And then orbital period on the x-axis. So it's a log scale, but this is a 1-day period and then out to 100 days. And what we're showing here is sort of the density, right? So where you see more points and where you see these thick contours, we see more planets. We find more planets. And then what's interesting is that there are these gaps, right? There are these gaps where you don't see many planets at all. So we have these hot Jupiters here, these sub-Saturns, which are a little bit smaller than Saturn, but there's not really that many of those either. And then there's this hot Neptune desert where you don't really see any close-in, Neptune-sized planets. Now that's interesting. Why do you get close Jupiters? You get close Earths, super Earths, but no hot Neptunes. And then if you take a closer look at this population of planets, these sub-Neptunes and super Earths that I already said are the most common, you can see that there's this dividing line. We call this the radius gap. So it's not only that most stars have a planet that's in between the sizes of Earth and Neptune, but it's that they either come in super Earth sized or sub-Neptune sized. So that's weird as well. You know, you kind of would expect that planets would just form in like a big jumble on average. You know, there must be something that's driving the fact that there's this gap in sizes between planets, or the fact that there's no close-in Neptune-sized planets. And so this all came into picture about 2016, 2017. These like missing planets tell us almost as much as the planets that we ultimately do find. And we've sort of had to, with each new batch of observations, we keep having to like redefine our theory to figure out exactly what's going on. So, you know, you could think about what forces, what like physical mechanisms would drive the exoplanet demographics to look like they do. And one thing is mass loss. Like imagine that a planet that has a lot of atmosphere loses it. You know, and after a certain amount of time, when we set our telescopes on it, we would see it and it would look different than when it started. So I want to show you an example of what that looks like. So on this plot right here, we're really zooming in on this super Earth and sub-Neptune population, which is clearly distinctly divided. So what if we focused on one planet? Let's say that these are all baby planets that are just born, and a lot of them are about 3 times the size of Earth, a little bit larger. Let's run the clock and see what happens if we account for the fact that because these planets are so close, 10, 20, 30 days, they're actually getting baked by their stars. They're really close to their stars. Obviously, a star is giving off a lot of energy. What happens to gas when you heat it up? It expands, right? So in your house, when gas heats up, the heat goes upstairs. This is why your upstairs is warmer than your downstairs. But if you heat it up enough on the planet, and it keeps going upstairs on the planet, eventually it escapes. It's no longer on the planet. It can leave the gravitational well of the planet. So if we watch this is over about 300 million years. What you can see is that this one planet that we look at is slowly losing its atmosphere. In the beginning, oops. Oh, could you put it on loop? Sorry about that. So in the beginning, these planets, there's a whole bunch of these sub-Neptune-sized planets. And within the first couple 100 million years, stars are really, really active. And what they do is just bake the atmosphere. while they're active. So it's something that happens over a relatively short period. There we go. Whoops. Okay, so actually we can just go on. We can just go to this slide. This is fine. Okay, so everybody in here has a brilliant imagination, I know, because you're in a planetarium on a Friday night. So what we're going to do is we're going to pretend that there are these planets up here that are a little bit larger, right in this region where I said that there aren't that many planets. So you start off with planets. What if all planets actually start close to this size, or most planets start close to this size? Over time, as you saw, as the star bakes the atmosphere away, what you would notice is that these planets would just drop down in size. They're losing their atmosphere, and then they appear smaller because they just have less gas. And by the time we look, they have dropped all the way down to a super-Earth or a sub-Neptune. And that's sort of the understanding we have. That's basically the understanding that we have right now. So you imagine a planet, if we were to shift this planet over to the left and have a Neptune-sized planet on a one-day orbit, it would just quickly lose its atmosphere and end up down here as a super-Earth. So we can kind of have this understanding of super-Earths that they're planets that could have started out more gaseous, but have just lost all their atmospheres. So they're like these stripped cores. So a lot of the super-Earths that we're seeing are just stripped, and a lot of the sub-Neptunes that we see have also lost a lot of their atmospheres. And, based on the mass, that initial mass, a planet's going to have an easier or harder time losing its atmosphere. Yeah?
Seeing the 100-day max orbit for all of these exoplanets is just kind of blowing my mind because we have such a longer one. Is this really the max that you've seen?
So this is like really zooming in on the majority of planets that we found. So yeah, if we were to extend this out a little bit, you have other planets. The Earth is out here. It's not even included on this. It's not even included. Yeah. But this right here accounts for the majority of planets that we found. Now, there.
Is it because the star is bigger, so it's pulling the planet's closer? Like, why is this the majority? Is 3.5 times closer, and even closer than that, the gas giants that are in our solar system?
For sure. So there's two answers. There's one that I know, and then there's one that I don't know. So I'll start with the one that I don't know. I'll start with the one that I know, actually. So the answer that I know is that the reason that we find close-in planets so much more frequently is just because they're easier to find. Now, I didn't talk about the detection methods, but I'll talk about two of them really quickly. So one is the transit method. If you've heard of TESS or Kepler, they are telescopes that are in space that are just staring at stars. And if you stare at a star long enough, and there's a planet orbiting it, the planet eventually is going to cross in front of it, and you're going to detect like a little dip in brightness. And if it's truly a planet, it's going to be orbiting on a period, and you're going to see that same dip in brightness over and over and over. So if you think about trying to find a planet using that method, it's going to be easiest to find planets that are bigger because they're going to block out more sunlight, or that are just close because you're going to see that period over and over again. You think about an Earth-sized planet that's at an Earth distance, 360 days. It's going to be significantly harder to see that orbit 3, 4, or 5 times, right? We're going to be talking about like 5 years looking at one star, as opposed to, a lot of these on a 10-day orbit. Within a month, you can tell, if there's a planet on one of those. So the other way that we find stars is called the radial velocity method. So, planets are orbiting stars, and we don't think about it like this, but the star also kind of orbits the planet. What happens is the star and the planet are both orbiting a center of mass that's common. So yeah, the planet does this. The Earth goes around in 1 year, but the sun also does its own small little orbit around the center of mass that it shares with the Earth. So if you stare at a star, you can see that shifting, that red shifting and blue shifting of light. And there it's the same thing. It's easier to detect the stars that have close orbiting planets and that are more massive, just because you're getting a lot of observations looking at that period over and over and over. So the fact that this is the first sort of regime that we've filled in, is really just a function of the fact that we have a bias for finding planets that are easier to find. So, when this talk is given in 20 years or something like that, and we've filled in way more, who knows? Maybe, it turns out that it's actually more common for planets to have, a small rocky planet at 500 days or something like that. But it's hard to tell. And, what's left off of this plot is any small planets, maybe Mars-sized planets are actually the most common, but it's really hard to detect a Mars-sized planet. They're not very massive and they're not very large. So we sort of have this detection bias. But with what we can do, this is just a huge chunk of the planets that we can find. Now, that's what I do know. What I don't know is why does it just so happen that this number right here, the majority of these planets, are in that range of between, 3 to 50 days? I don't know that. I don't know exactly why that's where most planets would end up forming. Because again, like I said, we don't have one. These are all significantly closer than Mercury. Mercury would be sort of somewhere over here, and it's pretty small, so somewhere down there. Does that make sense?
Yeah.
No, I just kind of rambled a little bit.
No, that was great.
Okay, cool. Sweet. Yeah.
Do you expect, though, that once we get the ability to observe planets that are on a much larger orbital period, that we'll see a lot more of them? Because basically none of our solar system is on this chart at all.
Yeah, exactly. Which tells us a couple things. One is that we don't actually know how common our solar system is. We know that it's not one of the most common things, right? It doesn't really show up, but we really haven't been able to fully probe that that regime.
Yeah, because for us to find a Jupiter on another star, that's the orbital period is so long we can't observe it.
Yeah, exactly. And what you're talking about now is like multi-year observation programs. There are people in my group who are doing just that, trying to link the presence of an Earth-sized planet, and not an Earth distance, but just one of these super Earths with a distant giant planet like a Jupiter. And, to catch Jupiter's full orbit, I think is 11 years, right? So it's like, at best, you can keep observing it for a handful of years, and maybe you can catch the star turning over, but you still haven't even gotten a complete orbit. So it's like, this is something that's going to take much longer to truly get. And, when you think about a further planet like Neptune or Uranus, which is even further and even lower mass, it's just much more difficult. So I think that the real way that we're going to start filling in all of these potentially missing planets that we just haven't been able to detect is going to be with direct imaging, where we can just start taking pictures of them and not have to rely on getting this full cycle of the orbit. But yeah, great question. Everything that we're talking about now is very foreign from our solar system, which we assumed was kind of the baseline. Okay, so how can we detect this happening, right? We see the planets being either super-Earths or sub-Neptunes. So, we can come up with the theory and say, oh, well, this is what's happening. It's easy to come up with a theory. It's easy to hypothesize. But to really prove it, you need to make the observations. You have to show some sort of empirical evidence that this is what's going on. And what you can think about doing, because this mass loss process happens pretty quickly. I know I said it was a couple 100 million years, which sounds like a long time, but for a planet and star that's going to end up being 10 or 15 billion years, this is actually happening extremely fast. But what we could do is we could check out these hot Jupiters that are closer, that must also be losing their atmosphere, but they're so massive that they will never lose all of it. So we should be able to look at these hot Jupiters and tell if they are losing mass in this way that we're predicting. And this is the project that I recently wrapped up. It was my first author publication, and it was this planet WASP 69b. It's a Jupiter-sized planet on a 3.5-day orbit, and we observed the transit, and what we saw was this helium gas that was trailing. So this planet, a gas giant, mostly hydrogen and helium, is having that hydrogen and helium baked, and it's escaping away, and the star is actually blowing it into a tail, which you can still see here. And the tail is at least 350,000 miles long, which is incredibly long. The gas is being heated to like 10,000 degrees Kelvin. It's traveling at 23 kilometers per second. Like, this is an extreme environment. And even at this rate, even losing this much atmosphere, it loses about an Earth's mass each billion years. So every billion years, it loses the entire mass of Earth. And over the course of its life, it'll lose maybe 10, 15 Earth masses, but it's a gas giant. It weighs like, it has a mass of about 90 Earth masses, so it'll never really lose all of its atmosphere. It'll never be totally stripped. It'll never end up being one of those super Earths. So this makes it an interesting planet to study. And I think one of the big takeaways as we continue to go through and learn more and more about planets is that we can't take a small amount of data and extrapolate it to everything else. You can't do it with planets. You can't do it with yourself. And this is something that I noticed in my life. So I do astrophysics now. I'm a PhD candidate, like I said, but I wasn't always. I used to just want to play football. I wanted to go to the NFL really bad, and I always knew that was what I was going to do. Here's a picture of me in 3rd grade. It's proof, both that I used to have hair and that I always was into sports. I was always, from very young, I just knew. I knew I was going to be a professional football player. I figured out in high school that I got better when I worked harder. I got stronger. I got faster. And I realized that, everything that you want to do in sports is really just based on working hard, on developing that skill. There are ways that you can edge out players that are more talented than you by simply working harder on technique, that sort of thing. And I ended up getting a scholarship to the University of Kentucky, and I played there. I graduated in 2013, and in my junior year, I ended up tearing my ACL. So, I felt like I was so close that I was almost to my dreams, almost to the point where I was going to be able to truly live out the successful life that I had always envisioned for myself. And then just almost in an instant, it all kind of evaporated. And I didn't have an idea of what I was going to do. It kind of felt like my life was over. It felt like I failed in the only thing that I was going to be successful in. And, I guess for the first time, I had to figure out who was I outside of being a football player. And I'd never really asked that question to myself. Who are you? What else can you do? What else are you interested in? I was very one-dimensional, sort of like how we were thinking about planets, right? We were this is our solar system, this is how stuff is. And we went into the search looking for Earth-like planets around sun-like stars. And it was a very narrow-minded sort of view. It was kind of like a constrained theory that we've slowly been prying back and opening up and prodding these new areas. So while I was actually rehabbing, I tore my ACL and my meniscus a couple of times. There was a lot of time when I was rehabbing and I couldn't really do anything. I was on the couch. And I started watching this show called The Cosmos. If anybody here has seen that, probably everybody. So both, but the first one that I saw was the reboot. And then I learned that that was a reboot. And I watched the original. And these are two probably the most impactful shows that I've ever consumed. And I realized that we live in an infinite universe. Like, I'm upset because I can't play football, but there's an infinite number of planets. And it helped me to like break out of the sort of depressed state that I was in. Just thinking that there are all these other planets, there are all these other stars, there are all these other galaxies. I can study that. Like, there may be aliens out there somewhere that are doing the exact same thing right now. There was this guy, and he's an alien. He's on planet HD 4521C, and he's playing alien football. It's a little bit different, but you can think of it as alien football. And they have like 12 Achilles. They're 12-legged animals, and he tore all 12 of them. And like, he didn't know what else he could do, and he's sitting on the couch and thinking the same thing, right? Like, oh man. And I don't know, just opening up those possibilities, it like freed me from this narrow-sighted tunnel vision that I had. There's all these galaxies. This is one of the James Webb Space Telescope images. This is amazing. Like, each one of these things is a galaxy with a couple 100 billion stars. If they're anything like the Milky Way, which they seem to be, most of those stars have planets. Surely some of them have life. And I decided that I was going to become an astrophysicist. I was going to start studying this. I was going to do whatever it took. I had no idea what it took, too, by the way, when I made this decision. So I Googled it. I looked up, like, well, how do you do this? How do you become an astrophysicist? Okay, so I need to get my PhD. And I was like, oh, well, I have an undergraduate degree. It wasn't in physics or anything like that, I'll tell you now. And I picked up the phone, I called a graduate department and asked one of the professors, like, how do I get into your program? There's this Russian guy. I'm not gonna do a Russian accent because I'm gonna butcher it. But he was like, yeah, you need multiple years of calculus, multiple years of physics. And I was like, I've heard of calculus. But I don't know the first thing about it. So I like reeled it in a little bit, and then I talked to the undergrad department, and they were like, yeah, so you still need some baseline to get into this physics program. And I didn't have that either. So I started at a community college in Indianapolis, and I was taking math courses during the day, and I was working at this airport at night, and I did that for a couple of years, and then I transferred and went to undergrad, got a bachelor's in physics, and then now I'm doing my PhD at UCLA in astrophysics. And sort of that entire journey is the same sort of like arc of discovery. I went through it with myself, from thinking that I could only do this one thing and sort of like wiping out the possibilities. You know, when I was in high school, when I was 21, if you would have told me that I was gonna be an astronomer one day and not be in the NFL, I probably would have like wanted to fight you. I'd have been so upset about it. And you know, one of the things that I've learned is that you don't know like what you're interested in. We're all unique in our own special ways, and there's like a lot of things in society that nudges us to be more like the people around us and to like shy away from the thing that is unique about us. And for me, one of my core values is like always trying to lean into that uniqueness and, you know, following what feels right, because we really each are unique. Like there's only one of me in the universe, which is like a crazy narcissistic thing to think about maybe, but it's actually true. It's scientifically true. Your DNA makes you completely unique. Okay, so let's keep going. Now, this trajectory, this journey of discovering things, of understanding things, applies not just to exoplanets and not just to my life and not just to your life, but literally to everything, right? We know that the universe itself evolves, and we come up with this theory based on the fact that we figured out that the universe is expanding. This was a crazy discovery. They didn't think this. Nobody knew this. They just thought that it was just around, and it had just always been around. And we looked out, we see that all of these galaxies are expanding, and then we see this thing called the cosmic microwave background, which is the afterglow from a Big Bang, like the universe sort of started inflating at some point for some reason. We're not really totally sure why. And we came up for a theory about this with this new revelation where, galaxies must have formed slowly over time. And in fact, our theories predicted that the universe started expanding the universe started expanding 13.8 billion years ago, but the first galaxies didn't start forming until about 1 billion years after that. That's what our observations told us. This is as recently as 3 years ago, 4 years ago, right before whenever James Webb Space Telescope started taking data. And of course, what James Webb has shown us is that there are these galaxies that are well before we thought that they could be. It wasn't 1 billion years after the Big Bang that some of these galaxies that we have been observing were around. It was closer to like 330 million years ago. So we're like way off. And if you were paying attention to the news, to the headlines, there was a lot of this, like the universe is broken. I hate those headlines. The universe is like, James Webb destroyed the universe, destroyed and it's like very clickbaity, and I get it because they need people to click on the links for the articles. But, it's really that same process. It's the same process of us making a discovery, coming up with a theory to explain it, and then the more information that you get, the more refinement that you can do. And that's what we do with these theories. And I think that headlines like that and painting it as though scientists, this is what they say, scientists can't figure it out. Like scientists are confused. Like we're just walking around, fingers scratching our heads, which is kind of true. I've spent a lot of my PhD doing that. But I think it does a disservice to the fact that it's okay to not know things. And it's okay to figure out what you do know and base your understanding on that. And then it's okay to learn something new. This is like a process that should be celebrated. Shouldn't be embarrassing that goofball scientists can't figure out what's going on. Our understanding of the universe itself is something that is requiring constant observations and constant updates to how we think about it. It's true for every science, and it's true for our lives as well. And something that is really important for me to emphasize that, as we go through our lives, that we keep that same attitude with ourselves, that you remember that there's a way that you think about your life. There's these expectations you have for yourself and this place that you think that you're going. And it's easy, we harden that understanding. And it's super important to keep that soft and be prepared to take it in a new direction. I think that that's something that has helped me immensely, especially with my mental health over time. And I think that it's really the only way that any of us can actually reach our potential is to sort of keep a soft, scientific, curious mind about ourselves. Yeah, so thanks. So there was a couple questions throughout, but are there any more questions? Literally about anything. If it's in the universe, then that counts. Yeah.
So.
I think we got a mic coming for you.
I can talk loud.
Go ahead.
I'll use the mic for everybody else.
So our mics catch it.
Yes, thank you.
1, 2.
Okay. So the chart with all the exoplanets that you're referring to is.
Let's find it real quick.
There you go.
One of these?
Yes. Mm-hmm. So I was wondering, are currently just studying what we see in our Milky Way universe, universe, galaxy, or are we studying else in the Andromeda Galaxy or other places as well?
Yeah. So great question, right? Because we know that we suspect that these planets are everywhere. I don't see any reason why they wouldn't be. But for now, we're sort of confined to our galaxy because it's really hard enough to detect these planets that are hundreds to thousands of light years away from us. When we start talking about the Andromeda Galaxy, for example, You're talking about something that's millions of light years away. So we really don't have the resolution to sort of pick out individual stars in other galaxies. Now, when one of them goes supernova, that gets really bright, and we can see that. We can see that star that's exploded against the rest of the stars, but we really don't have a way to truly probe what planets are orbiting the stars in other galaxies yet. And there was this one planet, it was a candidate planet. So I believe there's a black hole that is eating up some star that's orbiting it. And there were observations made that potentially were a planet that transited across that black hole that's eating the other star with respect to us in another galaxy. But I think it was on like an 80-year orbit. So you can't really graduate from a candidate to a confirmed planet until you have multiple orbits. So I guess we'll have to check again like in 80 years. And if they see that in 80
I'll
years,
see you then.
yeah, that'll be the first exoplanet confirmed in another galaxy. Now, we do know of rogue planets. So turns out there's actually way more exoplanets that are just in space, not orbiting any stars, than there are actually in systems orbiting stars. And the estimate is that there's trillions. So way more planets that are just out there free-floating rogue planets than ones that actually have homes.
Well, forgive me that I progressed. How do you detect a rogue planet?
Oh, so this is a great question. How do you detect a rogue planet? You're not detecting it, due to its impact on the star. It's not orbiting the star. Now, sometimes you can detect it relative to another star. There's something called microlensing. So one thing that we know that stars do, they're incredibly massive, and what they really do is they bend space around them. That's why planets orbit. It's not really about a gravitational pull. It's about a bending, a warping of space, and when you warp space enough, stuff kind of falls around it. So that's why we're orbiting the sun. So if things happen just perfectly, you could randomly have a rogue free-floating exoplanet cross a star that just happens to be behind it. And you can sort of detect this same sort of thing, this brightening that would be consistent with a rogue planet that was crossing by a star. The problem with that is you can never get a second observation because that planet isn't really orbiting the star, it's just shooting across. Now, another way to find them is by looking in the infrared. If you look at some of these rogue planets are pretty massive, and their temperature is warm enough that you can see them in longer wavelengths of light. So there are ways. They're a little bit tougher because sometimes you just have to get lucky. But they're out there and I wouldn't be surprised if our solar system had a planet that got kicked out. It's just very common when the chaotic early systems are forming.
So with the rogue planets, what makes it a planet if it's not orbiting a star? Because in my mind, planets always orbit stars. And
so that's a good, so now it's getting sort of semantic, right? Because it's like, so we say that what makes it, the reason Pluto is not a planet is because it's not fulfilling these three requirements. Massive enough to pull itself into a sphere, orbiting a star, right? And what's the third one? Oh, clears out its orbit. It clears out its orbit. So if you think about a planet that is a rogue planet, it's not clearing out its orbit, it's not orbiting anything. Probably massive enough to pull itself into a sphere, but it's definitely not orbiting a star. So, it's like, that's why we call them rogue planets. It's like its own category, right? A free-floating planet. Because, maybe they formed in a system and got ejected. Maybe they just formed on their own. There's some evidence that you could just form a planet in the right circumstances, a really a massive gaseous planet. You just form it. And so that's good though. It's like, we define things prematurely, and in astronomy, we don't change the definitions. We just like hand wave it, call it something else. Yeah, so there's still planets, but Pluto's not.
Are most of those gas planets, or are they rocky? Because you said there's trillions of exoplanets.
Yeah, so the ones that we've detected are definitely massive gaseous planets, but undoubtedly, and probably in much greater number, there are going to be tons of small planets that get kicked out. Simulations show that Mercury is probably going to get kicked out of our system eventually, in billions of years. And like, how do you detect a Mercury floating in free space? We can't even detect Mercury's barely around the actual stars. Yeah.
How does a planet get kicked out of a solar system?
That's a really good question, right? Because when we look at our solar system, things seem normal, right? It seems stable, like all the planets are just orbiting. It's just, how is anything getting kicked out? But realistically, whenever you have multiple gravitational bodies that are orbiting one another, it's never actually stable. It seems like it's stable. So we would call our solar system right now semi-stable or quasi-stable. It's like stable for a while. But in billions and billions of years, after a really long amount of time, planets, they tug on each other a little bit. Like every once in a while, Jupiter and Saturn actually tug on the Earth a little bit, and they change the Earth's orbit. So one of the reasons that, are you familiar with ice ages? That like sometimes the Earth has periods where it gets really cold, or it gets much warmer. And there are multiple reasons for that, but one of them is because the Earth goes through cycles where sometimes its orbit is more circular, and sometimes it's a little more elliptical. And this is coming from Jupiter, like tugging on us. And when it's elliptical, sometimes we end up a little bit further away from the sun for a longer period of time. And, every 100,000 years or something like that, we experience something similar. And over enough time, Jupiter doing this to enough of the planets, and the other planets doing it to themselves, it can just like knock things out of order and send like Mercury in a little bit too close to the sun. And if it gets a little bit too close, there's a chance that it kind of like whips around the sun and just gets shot out, or maybe collides into Venus, or maybe even Earth. Now this will be like way, way, way in the future, so we don't have to worry about that. But this is what happens in systems. There's just chaos when you have too many things that are orbiting and pulling on one another.
You mentioned that the astrophysics and astronomy and everything is always in flux.
Yeah.
And there was a guy, 2 or 4 lectures ago, I think it was a JPL guy, just a kid, probably wasn't 40 yet. And he said that everything he'd done for his doctoral dissertation, for his PhD in his early mid-20s, all wrong, all been disapproved, and there hadn't been 12 years in my life.
Yeah.
So it's just, you guys are just guessing.
Well, let's say that we're making very educated guesses with the information that we have. But yeah, I mean, that's all you can do. That's all you can ever do is try to go off the information that you have. I mean, I guess it's frustrating if you always want to be right. If you want to be right, and you want to be right forever, and you want everybody to know that you're always right, then that is frustrating. Because, if you're doing the right thing, you're like asking questions that haven't been asked before, sometimes you're going to be wrong. And that's okay. It's okay to be wrong. That's how we, I mean, I think you're talking about Constantine that was here. They give the talk. Yeah. I mean, I hope that I'm never wrong. But if I am, I guess I'll have to. Yeah, I'll try to put in something that can't ever be disproven. Yeah.
Could you postulate on how a planet like WASP 69b even accretes to begin with, if it's so close to the star that it all gets blown off once it's accreted? How did it actually get to that state to begin with?
Yeah, so there are really two kind of formation pathways for hot Jupiters. Let's go to that slide. So one possible is called in situ formation. So maybe they do form that closely. Now, that's hard for me to believe for the reasons you said. How is something accreting that much that close to the star when we know that early on the star is even more active than it is, when it settles down? But what does, I think, make a lot more sense, at least to me, is that the planet accretes far enough away that it gets massive enough before it gets close. So by the time it gets close, yeah, it's still losing its atmosphere, as we see with the observations that we make on hot Jupiters, but it has enough mass that it can hold that gas tightly enough that, what slips away isn't enough to considerably drain it. So it can never actually be stripped, which is why these hot Jupiters are kind of a unique test bed for this theory of mass loss, because we can see them and they're never going to be totally kind of drained dry of the reservoir that they have of gas. Oh, yeah.
Solar systems yet that somewhat look like our solar system?
Not really. Not really. It depends what you mean somewhat like. We have found stars that are much less massive, called M dwarfs, that have like the same number of planets. So they are maybe like 8 planets, but they're all packed in really closely, like much more closely than our system, all within Mercury's orbit. So we actually have never found that. And I guess I should plug this because you always hear that astronomers found an Earth-like planet in the Goldilocks zone even. But it's never truly Earth-like. We have never found an Earth-sized planet at 365 days or around there, around a sun-like star. We find Earth-like planets that are closer, and the habitable zone can be closer for lower mass stars, but we've never found even a true Earth analog. So we haven't yet found. It's not that we won't find it. I think that we will, but we certainly haven't yet.
Are all the hypotheses associated with the sizing that you showed attributed only to stars? All your hypothesis centers around, is it burning off the stars? Is there any competing hypotheses?
What do you mean? Competing?
You're showing, like, you have models, right? Origins of the coalescence to those two sizes that you showed, right? They all involve stars, at least what I can see from.
So
outside of stars, like in theories, competing theories.
For planets to form outside of stars?
Yeah.
Without stars?
That you see here. Yeah.
Okay, so the question was, are there like any competing theories that are basically not involving stars?
Yeah.
Right? So the planets are still orbiting stars. So that's not what you're asking, right? Or is that what you're asking too? Like, because there can be planets that don't orbit stars. These are called free floating or rogue planets, and we still think that most of the time planets that are free floating did form orbiting a star, and maybe they got ejected. But it is possible to form a planet, just out in space under the right circumstances. But for all of these planets are orbiting stars, and we attribute the shape of this demographics plot, like this radius gap, and this hot Neptune desert, to the stars actually affecting the planets so much that it kind of sculpts them into sizes that are what you see in the big jumbles. But yeah, for like most of the time when we're talking about planets and we're really studying them, they're going to be planets that are orbiting stars, because those are the ones that are easy to find. It's kind of hard to just find random planets out there, and even if you do find them, it's hard to continue studying them. Hi.
How did you manage to look inward and find a new sense of self when you had that juncture in your life? And can you compare that to, this is my hope, that you could compare that to a scientist who is certain about their findings and publish them, and then they have to turn around and look inward at their own findings to grow because those findings are changing. If you could talk about those two things, that would be great.
For sure, for sure. That's a really good question. So I think for me, what made it a little bit easier to grow, if you will, was not having any identity. Like once football was gone, once being an athlete was off the table, that was all that my life was about. So it's almost, I think, easier. It's a very sad time. It's a very depressing time. But it's almost easier. It's like when you're a child, it's easier to learn new things. It's easy when you have nothing to latch onto, you have nothing to hold on to, it might be a little bit easier to find something, to explore and figure out, who you are, what you're really interested in. And ironically, as a scientist, you sort of face the opposite problem because you start to really figure things out, and you start to, what you find starts to actually become a part of your identity. I'm a scientist that studies planets, and I know that planets are like this. And I published this paper, and I published a lot of papers actually. And this is how we know planets are. And then there are rivalries. There are heated rivalries in astronomy, and really in all fields, because people do get attached to their ideas as a part of their identity. And I think that that's sort of something that I guess we all as humans have to deal with. The fact that these things that we do, the way that we see ourselves becomes super interwoven with our job or what we feel like we've accomplished. And it's almost letting go of some of that is kind of like losing your identity. And people don't want to do that, and a lot of scientists are no different. Scientists are just people. So I think that that's something that scientists also have to. If you're really living up to what you say that you're doing as a scientist, you have to be okay with letting go of what's wrong. But I don't think scientists are really any better at doing that than anybody else. Yeah, thanks for the question.
I'm sorry you mentioned this, I came in a bit late, but those exoplanets that are creating those tails around their host stars, I know they reminded me a lot of comets, right? And I know comets, to understand what they're made out of, right? We study the tails, right? Is it possible to find out what the atmosphere of a planet is like by looking at their tails, or is it too faint?
That's a really good question. We call these comet-like tails. And the thing is, with a hot Jupiter, you have to be losing a lot of atmosphere to get a tail like a comet as a planet. You think about what a comet is, it's really a small asteroid that has some ice, and as it gets closer to the sun, the ice kind of melts, evaporates, vaporizes, and it gets pushed away in that tail, which is a little bit different than what's happening on a planet. A hot Jupiter is mostly hydrogen and helium, which is a pretty light gas. And you have to heat it to extreme temperatures to get it to escape. And then what happens is there's a stellar wind. We don't really think about that, but the sun doesn't just give off energy. There's also actual stuff. There's material coming off of the star. And that material runs headfirst into the atmosphere that's escaped and forces it into that tail. But it's all hydrogen and helium. Those are the light elements, so they're the ones that escape. And in a gas giant, those are the dominant elements that are abundant there. So there's not really anything else there. This tail that I showed with the animation is basically completely, let me see if I can get to it. This is all helium. our observations, we were looking at just helium. So all of this is just helium. There's nothing else coming off. There's probably hydrogen as well. There's definitely hydrogen, but we didn't see that because we were only looking at the helium. So, however, what you're talking about doing, studying the atmosphere of a planet, is something that we can do, and we do it with JWST. Just wait for that planet to cross, and some of the starlight gets blocked out, but some of it goes through the atmosphere. And that's probably how we're going to find life or signs of life. It's going to be through that sort of transmission spectroscopy, where you see, oh, there's water in this atmosphere, or there's carbon dioxide, whatever it is.
So, piggybacking off of Lisa's question there, because I was wondering, like, since you mentioned the sun is solar winds hitting it, so really there's two parts to this. One, I was wondering, like, are you observing this with visible light? Because you said the Tech telescope is being used to observe this from Earth.
Yeah, observe what? Are you talking about this specifically?
Yes.
Yeah, so we made these observations with Kevin.
Okay, so it's visible light is what we're looking at.
No, this is actually infrared.
Okay. Just want to be clear. But the other part of that question, which you're curious now, is like, if the solar wind is hitting that hot Jupiter's tail, are you seeing it as auroras a little bit? Or like, how like the sun's particles can ionize our atmosphere and we can see that kind of thing? Is that doing that with the tail?
No. So that's not what we're looking at here. But that sort of behavior, right, which is coming from these charged particles that comes from the sun on the Earth, it follows our magnetic field lines, crashes into the atmosphere, and then when it hits certain molecules in the atmosphere, you get like this bright green flash of light, or a purple or a pink flash of light. But that is not really what's going on here, and that's also not the wavelengths that we're looking at. We aren't observing visible wavelengths. This is a near infrared spectrometer, so we're only observing in the infrared. We would have to look in different wavelengths, but I don't think that we would see anything like that for a planet like this. I suspect that you definitely see it for some planets, but not these planets, because what's coming off is hydrogen and helium. And when we see auroras, it's not charged particles crashing into hydrogen or helium. They're actually crashing into heavier elements. So, slamming some protons into this hydrogen or helium tail isn't going to give that bright aurora like we see. I mean, even on Jupiter has auroras as well.
With like the hot Jupiters, does it like happen where the Jupiter eventually gets like so close to the sun it like completely just disappears?
Usually, no. Usually, it's not losing mass fast enough. But we have found a couple really interesting, super close, super massive planets, like a rocky planet that's, dozens of Earth masses, which that's peculiar, because a rocky planet, they really don't get that massive. Once you start to get that massive in your core, you start accumulating a bunch of gas. So there are some that we find that we do think are stripped Jupiters. So they're going to be just really, really dense, really rocky, small, massive planets. And, that's the thing that you have to remember, because we always say, there's no surface on Jupiter. If you went to Jupiter and tried to land, you couldn't. There's no surface. There's maybe deep down, there's a rocky core. But if you could just start peeling off a lot of that gas, you would lower the pressure inside and cool things off a little bit, and there would be a core eventually that would be able to exist if you could blow enough of the atmosphere away. So there are planets that we think are completely stripped Jupiters, but I know that when you learn about it, it's all gas. But you could never blow it all away so that it was nothing. You know what I mean? Eventually you would get to a point where there was a core.
a follow-up on that question regarding the sub-Neptunes. When they're getting their atmosphere blown off, does that mean they hit a stabilization point when they become a super-Earth? And if so, does that imply that we have a tendency to find sub-Neptunes orbiting younger stars and super-Earths orbiting older stars?
So good question. There is right, this, when you think of a sub-Neptune, you've got a rocky core in there, and you had enough to accrete some amount of atmosphere, some amount of like hydrogen and helium, and the amount that you get obviously depends on how massive that core is. But when you think about the rate of occurrence of sub-Neptunes or super-Earths, it's not really, there isn't really going to be an age dependence because it happens so fast. It happens so fast. It's like it continues to happen over the course of the entire lifetime of the sub-Neptune, for example. But our understanding of mass loss right now is that basically, if it's going to happen, if it's going to be totally stripped, it happens within the first couple 100 million years. After that, the energy output of the star changes and it like calms down a little bit. And so it'll still continue to bake away some of the atmosphere, but not to the point that it would get stripped. So whether you looked at 3 billion years or 10 billion years, you should still see the same ratio of super-Earths to sub-Neptunes. But that's a good question. And I guess the key there is that it happens so quick that it's so extreme that it either completely gets stripped or it doesn't.
So you know how there are these, those stripped planets that used to be gas planets, orbiting close in, but their atmospheres got stripped away, and they're rocky planets.
Mm-hmm.
How can you tell that those huge massive cores are not just, gas giants?
So like how, if we look and we see that it's a really massive planet, how do we know that it just isn't still a gas giant after all? Is that what you're asking? Good question. So what you really need to do is you really only need two parameters. You need like two properties. Mass is one and size is the other, right? Because if you take something that's really small and really massive, you know that it can't be gaseous, right? Like, because you can divide the mass over the volume and find the density. So, for example, do you know the density of Saturn or Jupiter? These are really low density planets. Saturn, theoretically, could float in a bathtub of water. It's that low density. And it doesn't mean it's not massive, right? It's very massive, but it's really, really large. So that tells you that there has to be gas there. There has to be a bunch of gas. Because if it was all rocky, it would be like so massive that it's completely unphysical. So when you have a small object that's really massive, you know that it can't be because there's a bunch of puffy gas. It kind of has to be because it's really dense and rocky. Does that make sense? Good question. Mm-hmm.
And this will be our last question, but I know you're working with exoplanets right now. Mm-hmm. What do you plan to do once you get your doctorate and everything? I just want to know what you think you're going to be doing in the future.
Yeah, so I love doing research. So it would be cool to be still involved in research, but I also really like doing science communication, engaging with the public. So I think it would be cool to get to figure out something in my career where I can spend a lot of my time engaging and educating, and maybe doing some exoplanet research on the side to make sure that I'm not getting like proven wrong or anything like that. Yeah, and I think, did you have one? Do you still have the mic? Oh, can we do one more?
So slowly over time, are like solar systems and the stars and the planets orbiting them, are they moving like around in space? Like, do they change positions?
Oh, for sure, all the time, right? The planets orbit the star, and the star is orbiting in the galaxy. And a lot of times, some of the planets probably have moons, and their orbits are changing a little bit. But yeah, these things are always moving. They're always in motion. Yeah, just like the planets in our solar system, just like the Earth. Cool. All right. Well, yeah. Thanks for having me, and thanks for coming out.